And then the last talk is by Per Lindholt from DNF, winch manufacturer from Norway, and basically also new to this community here, relatively, I understand.
Very much.
Please.
This is my first visit here, and we're approaching Friday afternoon, so I've lost my identity. I hope I'll be able to take you through this anyway. This is about industrialization of fluid power ground stations for pumping kites. A few of you may have heard about fluid power ground stations. We could also call them hydraulic ground stations. It's about how do you do the power transmission. Oh, sorry. Yes. Better now? I don't have to start over again?
No.
Thanks. Yeah, this is a cooperation effort between my company, DNF AS, and Imenco, a Norwegian industrial company. But before I dive into it, I'd like to take you back a little bit and show some history. This is the very short history of Norwegian venture company Drive. If there's one who has heard about it, then it's luck. But there was invested approximately, say, 15 million euros at the time in developing hydraulic drivetrains for conventional wind turbines. So it started out in 2005, setting up test benches, producing electricity with hydraulic transmissions. There was built, or not built, but two turbines, one 225 and one 900 kilowatts, were equipped with hydraulic transmissions based on standard components, and some conceptual designs were developed, 5 megawatt and 3 megawatt. Part of that, very importantly, was developed with a similar hydraulic motor and pump technology that I'm going to show you in a minute. The company was closed down in 2013, and some may remember, some same hair color that I have, that in 2012 was the deepest dive for wind turbine industry for decades. So if you had spent like 100,000 whatever currency on buying Vestas shares at the time and had kept them, you could withdraw now and live safely ever after. In 2013, 3 of us in that company, we were employed engineers at the time, we bought out the hydraulic technology that we had developed, and we formed DNF. And we joined forces with Imenco, Smart Solutions. And Imenco is today a 100 million euro company, Norwegian, with business in the hydraulic industry, business in subsea cameras, subsea data transmission, hydraulic motors and cylinders, supplying oil and gas, supplying offshore renewables, aquaculture, marine and naval, stuff like that. And together with these guys, and together with MacGregor Norway, we developed the first motors with, and I couldn't call them digital motors. I learned yesterday that we should call digitized motors. That means motors and pumps where we control individually each cylinder by electronic means. So each cylinder in a large machine has valves that you control individually by electronics. That gives you a number of freedom. So we developed a winch drive on that. That is what you see to the right, lowest, and learned how to control it. And a few people from Ampix visited us at the time, like 2 or 3 months after we had it up and running for the very first time. And we continued for half a year and ended up having that working. And it's actually available on the internet. You can see videos today of the performance. What we also were exposed to at the time was that there might be a market within airborne wind pumping kites. And what we learned then was that if you look at top middle, there's a hydraulic diagram. I don't know if anybody can read such a diagram, but on the left-hand side is a winch driven by one of our pump motors. On the right-hand side is a motor driven by or driving with an electrical motor or generator, it doesn't really matter. And in between, what is on the top is a hydraulic accumulator, basically a supercapacitor or a capacitor just in hydraulics. So there's an isolation between the two. Such schematic was something that we had worked with before, and it's exactly the same schematics that we used together with MacGregor for the crane winch. And that crane winch has the characteristics that it was heave compensating, so up and down and up and down and up and down. And that is what we do in a pumping kite, only the cycle is slower. And whether we take in power or put in power, or we take out power, doesn't really matter. It's just the arrow pointing in the other direction. We combined that with what we learned from the wind turbines, and underneath here you see the comparison between the hydraulic solution and the electrical solution. If you look at the electrical solution at the bottom, for a pumping kite, you would start out with a gearbox, then you would have a generator motor, then you would have an AC-DC converter or DC-AC converter to control that motor so that you control the kite. Then you have some kind of storage, capacitor bank in this case, and you again do need some DC-AC because you need to deliver something to the grid. And by the way, sometimes you also need a transformer to deliver a decent voltage. That's not something we're talking a lot about, but if you're looking into a wind turbine park, all wind turbines in the back end of the nacelle or bottom of the tower has a transformer to get to, say, 30 kilovolts. And if we look at the line above here, what we're doing is that we are taking our large motors, the digitized motors, and we're driving the winch directly, so no gearbox. And that pump motor is supplying our accumulator, our hydraulic accumulator, and store energy. We use that energy on the right-hand side, putting it through a conventional hydraulic motor, which drives an alternator, a synchronous generator. And the idea of using a synchronous generator is that we don't need power electronics after it, and it's a very robust solution. It synchronizes with the grid frequency, so spins at constant speed. That makes it easy to give our swash plate motor good operating conditions. It also means that we could actually transfer energy back and forth with no major deal. And one thing more, such synchronous generators are available up to 10 or 15 kilovolts, not watts, but volts, which means that in some cases we obtain also the benefit of having a higher voltage for a local park. Yeah, there has been a little bit of discussion among some people, do we really need the smoothing? Where do we need it? And the question here is, what are we actually selling? And that was what we asked ourselves. And we are, of course, selling electricity. That's a product at the end of the day. And the electricity companies don't care much how we generate that. Electricity is the mean. And that electricity has some characteristics and some qualities. And forced to be as what is on the left on the top may not be the best quality. This is what it might look like. This is kind of a Donald Duck design. We've taken out all the hoses and pipes and stuff, but there are a few key components. And this is pretty much what there is. There is a cylinder accumulator, there is nitrogen energy storage, there is a generator, driven by a hydraulic motor. There's a winch and a winch drive. And then there's a cooler and a hydraulic tank. The key technology in here is actually the winch drives. So what we see here is two motors from the Emenco motor range. So what is on the far left are standard motors. They've been produced for 60 years, not without changes, but gradually and very slowly improving. So there's a lot of reliability and there's a lot of history. It's all built out of standard components. It's very modular, so there's motor range, but built from the same components. What we have added is the valve technology, that is what you see in the middle, and electronic and control. And by combining all the standard components and the new technology, we obtain features that are sufficient to drive the winches at a very high efficiency. So we obtain controllability. We have a very high efficiency also at part load. We have minimal idling losses. We have a superior power to weight ratio, a torque to weight ratio, and torque and speed are controllable. Yeah. Industrialization also means simplification, and that's how we reach efficiency, because we have direct drive, there are no gears, we have very large winch diameters, and that's one of the first things you're asking for. There's a large winch diameter because you need to accommodate a bending that is not too rigid to prolong the lifetime of your tether. The components we have are suitable for ground station with nominal powers from 100 kilowatt, and that was some of the pilots we looked at before, and up to plus 1 megawatt based on Emenco's standard motor program. Cost of torque is lower than for the E-solutions, and that allows for harvesting larger variations of power and make it economical. It doesn't mean that you have to do it, but it's an option. And when we talk about optimization, and we have seen some talks on optimization, it's important to remember also the characteristics of the ground station in the total operational scheme, because we can use characteristics of a ground station and characteristics of the kite to match each other, and all of a sudden we obtain better system solutions. We also have, in the similar way, we have overspeed capability. So even if we have a rated speed below which we have a very good efficiency, we can also allow a higher speed, but then sacrifice efficiency because we have more oil that need to go through, but maintain torque, but have higher speed on the cost of efficiency. So that might be a help to mitigate wind gust, the effect of gusts, so that maybe not avoiding to derate the wing, but don't have to derate it as fast. But depends. That's a case study.
We should
Time
to an
running. Okay. The storage. Yes.
Well, we should be at the coffee break.
Okay. I'm sorry. Storage here. Round cycle efficiency of 95%, proven from the offshore industry. This one is very important. If you look to the right, each transformation is about the same cost. We just learned that from Rishika's work and our own studies. So for electric, we start out with a gear, we have a generator, we have AC/DC, and then we have a smoothing capacitor, and then we are down to rated speed, DC/AC, and maybe a trifle. On the right-hand side, we have the hydraulics, and we have starting out with 200% of rated, and then down to the smoothing accumulator at half cost of the capacitor, and then the hydraulic motor and generator. Guess what is the cheapest? This is scaling, and just take the upper second line. euro per kilowatt, starting out at 100% with 180 kilowatts. At 1,000 kilowatt, we are at 55%. At 3,000 kilowatt, 3 megawatts, we're at 51%. What is shown underneath is not cost distribution, that's weight distribution. Sparse materials. What do you use? Not only weight, but also what materials do you use? We use iron. It's one of the most plenty material on Earth, and it's one of those that are easiest to reuse. So, summary, less cost. We're backed by industrial experience and industrial capacity, high efficiency through less transformations. We have eternal life in our storage, no degradation. We have a technology that is scalable with the components that we have, and it's available. Sorry for exceeding the time and stealing your coffee break or part of it.
Thank you.
Questions?
Maybe a short one. Yes, Jochen.
Technology?
It's a similar technology. The difference is that we used forced activation of the valves, where Artemis technology, which today is owned by Danfoss,
Yes.
is opening and closing from the pressure differences.
Yeah.
But we use forced activation, and that makes our solution less optimal at high speeds, but better at low speeds.
Okay. Thank you.
Thank you. Maybe then one remark from me that the third presentation track switches now room from Solano to Nordes, and that will be from room 04 to room 01 on this level here, just that you know. And after the coffee break that is outside now, we have our last session track with 5 presentations. Then there is farewell and also the poster awards ceremony. So see you later. Yes, here in the auditorium.